Yeah, good morning to all. Uh, we are in this third day of our GAN course, that is on combustion theory and applications. In the first 2 days, I had given the concept of thermodynamics. Then we tried to bring the thermodynamic concept into combustions. Then we also studied some fundamental concepts of combustions and chemical kinetics as well. Then we tried to merge fundamental equation of thermodynamics with the chemical kinetics. When we merge them, we try to frame a set of equations that are that can be modeled analytically with uh, mathematical forms such as mass conservation, species conservations, momentum and energy. All these equations can be derived. Additionally, we also emphasized about reactors in which we can link the closed and open system concept of thermodynamics through this reactor, so that equations can be effectively modeled. Then we also give some fundamental concepts of combustions such as adiabatic flame temperature, equilibrium products of combustion, then we introduce heating value of fuel, all sorts of things, and of course equilibrium constants, rate coefficients. All those parameters are basic requirement for the combustion studies. Now moving further in this lecture, which is entitled as Thermodynamics of Reactive Systems, we will move further, and it is part 2. We will try to see that although we have given a coupling systems in which the reaction kinetics of combustions can be linked to the concepts of closed system, open system equations involving first law and second law. But then how to frame that equations for a reactive systems? And in fact, conservation methods of reacting flow helps us to frame the analytical modeling, and in fact most of the combustion modelings, whatever software you use, we try to see how whether we try to evolve that these equations needs to be solved. Three fundamental equations: mass, energy and momentum. These are typically used in the fluid mechanics concept. Thermodynamically, we say that first law, second law analysis has to be satisfied. Third, bring combustion into pictures. Now when you combine three things together, fluid mechanics governing equations, mass, momentum, energy, and uh, and this thermodynamics equations like first law, second law and entropy equations. Both the things we integrate with chemical kinetics uh, and uh, and reactions, chemical kinetics of reactions. Then when you couple them, we frame the combustion equations, and here we call this as a conservation methods, that means framing the reactions. And here I need to emphasize that as far as fluid mechanics is concerned, we are really bothered about mostly on momentum equations, but you will find that momentum equations is not that significant when you do combustion, because it's instantaneous events, and there is no velocity component uh, involved in this picture, as long as we are going for high speed combustion. Then we will try to introduce this multi-component diffusion. In our last concept, we talked about Fick's law of diffusion, which tried to evolve that how two species combines each other, and based on this we find the flux equations and specifically for species flux. Here, multi-component diffusion is another concept which evolves as that in a combustion environment, it is not only two species that combine. There are possibilities, because if you see this room as if it is a reactor, and fuel and air is initially there and combustion has happened, we ignite. So, we will find n number of species that comes out from these reactions. I have already mentioned that there are global reactions, there are elementary reactions. Possibility of elementary reactions are based on the fuel and air constituent species, and the reaction can happen at atomic level, molecular level. It can also happen if temperature is so high, it can happen in ionized level. And in this process, since it is a closed environment, or reactor is a closed environment, we can see that there are possibilities that sometimes, depending on the initiation of reactions, some zones are too hot, some zones are too light. This is typically what you do in diesel engines when fuel is injected. So in some zones, reaction the phi, which is equivalence ratio, is lean, rich. So we cannot predict the temperatures to be uniform throughout that reactor or throughout that domain. So for that reason, different species are formed. They try to combine among themselves depending on pressure, temperature conditions in that domain. So when they combine, the concept of Fick's law drops in, where we have to include that concept of diffusion coefficients. One species tries to diffuse with other to make a recombination. So this comes under this multi-component diffusion, because there is no two species, there may be n number of species, and possibility of combination can be many. Another important term, we call this as a conserved scalar. This conserved scalar is another concept which is introduced mainly to tackle these conservation equations. What is that conserved scalar? It is a generic term. So previously I told you about this equivalence ratio phi, and this equivalence ratio phi changes from, depending on the flammability limit and combustions to happen, it changes from 0.8 to 1.2 in a typical engine environment. But what happens that as far as when you say the fuel air mixture is already pre-mixed, the role of equivalence ratio makes some sense. Okay, and when it is a non pre-mixed, means air comes separately, fuel comes separately. So means equivalence ratio changes in this combustion domain. It cannot be it changes drastically. So some zones the fuel is completely rich, some zone fuel is completely lean, because they are not mixed properly as per the stoichiometric conditions. So such cases, what is the criteria that fuel remains its identity? Fuel remains its, mainly fuel when it is pre-mixed, fuel remains its identity through the value of equivalence ratio. We say it is lean or rich. But lean rich means we know at least the percentage of fuel and air combination. But in an environment where it is a non pre-mixed, the role of phi does not seem to be appropriate. So for that reasons, we try to find out another parameter. We have to find out another parameter apart from phi, through which we can keep the fuel identity or one parameter to be conserved everywhere in the flow field or in the domain. So that term, equivalence ratio, is one kind of conserved scalar, but it is not true for all kinds of situations, pre-mixed or non-pre-mixed. So that way we define a term conserved scalar for an which has to be taken into account through these conservation equations. In other words, we try to mean that conjugate scalar parameter is linked to equivalence ratio phi, but reverse you are not going to do. That is what the mathematical representation talks about. Then already I told you about equilibrium products of combustion. So through these products of combustion, we try to see various species are formed: NO, CO, NO2, CO2, all species, irrespective whether the mixture is rich or lean. When these species are formed, that's the reality. And in our chemical kinetics term, we say these species are going to be formed whether mixture is rich or lean. I had given you some standard equations in which we do this, we find the stoichiometric coefficients by balancing the atoms. But in terms of chemistry point of view, we want to see that because if you look at that curve, you will find the NO formations comes in both lean as well as rich. CO formation is also formed in the lean and rich. But is there any mechanism in which we can say NO formation in lean region is because of this region, NO formation of CO and NO in rich region is because of certain region. So through these things, we will try to evolve the typical uh, uh, typical formation of compounds like CO, NOx, why it is formed, and if it is formed, whether it is due to temperature, due to pressure, or equivalence ratio, or for any other reasons. What is that mechanism, why it is formed? If you say it is because of temperature, then why, if you say that normally in our RNAs equations we say reaction is mainly governed by the temperatures control, because it is a main function of temperature. If at high temperature NO or CO is formed, why it is forming in low temperatures? Because our curves indicate that. So those things we try to find out what is the mechanism of reactions. Now apart from this, one important uh, as a case study, I will try to emphasize a hydrogen oxygen reaction system, which is hydrogen is a very good fuel, oxygen is a oxidizer. So when you want to have these combinations, what are as a case study I will try to explain that what are the possible elementary reactions are formed, and through these reactions how we can say whether of course in this combination you will not have CO NO formation, but it will talk about what are the cause of these reactions, and this will emphasize whether it's a very good practical case where you need to demonstrate the chain reactions, chain initiation reactions, then chain reactions, chain termination reaction, all reactions can be modeled. So this is the overview of what I am going to discuss here. So to start with, this is conservation of methods for reacting flows. So there are three ways one can model. One is steady one dimensional planar geometry in which x coordinate is only there. Second one is steady one dimensional spherical geometry where r coordinates we need radial coordinates, and third is two dimensional axis symmetry. So typically this is schematically one can show like this. Now what are these connection with our combustion modeling? So for example, when you have planar flame, it's like a plane, the flame like in SI engines, a flame is initiated and tries to propagate in the domain. So that's a planar flame which moves in that domain. Now if you to why it is a spherical dome, why it is necessary? Because in a diesel engines we inject the fuel through injectors. Fuel comes as a small droplets, liquid droplets initially, and with high environment the droplets evaporates. Means it's like a fuel is can be assumed to be initially at certain diameter, and when it evaporates it vanishes, means its initial radius, if a droplet you can design at its initial radius with r0, that vanishes when it evaporates. So that way this modeling we can say it's a spherical flame. Of course that is at fuel level. Now there is another way we can think about this axisymmetric jet. This fuel, when it is injected, it is with certain pressure. Normally this we call it as fuel injection pressure, and it comes as a jet. When it is jets, it has certain momentum, initial momentum, and when it enters to the combustion domain, because of its initial momentum, the jet, it creates a free jet within the domain, and this when it comes, at least if you say assume that this is a kind of a diameter of fuel nozzle, it comes a jet, and this jet has some free boundary, and with this momentum it can go with a maximum axial distance, and across this we will have, because along its axis the strength of fuel is very high, which is rich, and when you go outside it becomes linear. So this is how we say fuel comes as a jet. So that is the reason these are the three kind of situations. Normally or classically we call this as a analysis of conservation methods. So first type of things when you talk about conservation equation, which is mass. In fluid mechanics term, CFDs, we usually focus on mass, because the initial the gas does not break into species. When it species, then it becomes there will have two equations, not only mass conservation, you will also have to species conservation equation, that you have to frame based on the Fick's law. And there are two types of velocities through this we can happen, one can define. One is the bulk velocity, other is the diffusional velocity. The fluid velocity is referred as a mass average bulk velocity. That means you take entire mass involving this as a bulk velocity, and difference between the species velocity and bulk velocity is diffusional velocity, which means that when after the combustion is done, species are formed, they have their own velocity, and when you take difference between the, because they travel much faster, and difference between species velocity and bulk velocity is the diffusional velocity. So talking into this and multiplying it by its mole fraction factor, we get the species conservation equations. So this is how we frame this equation, overall mass conservation equations here. And when you say species conservation equation, this rho stands as a global density of the mixture. Now when species equation comes, we take this equation is reframed with respect to that species based on its mole fraction, and here this total velocity is the combination of this. So through this we get two equations needs to be solved, overall mass conservation and species conservation. This is again a continuation of same mass and species conservation. Through this we can get two main equations, mass conservation equations and species conservation equations. To address these species conservation equations, we have to take the help of the Fick's law for a binary mixture, if it is a two species binary mixtures, and we can frame for each species what species equation MA and MB. the next thing, this is how a mass conservation equation is evolved for in a domain that which is 3 times planar or axisymmetric or spherical coordinates. Then for that also, again moving further, we also look at momentum conservations, and this momentum conservation has not direct relevance to this combustion domain. Sometimes people ignore these momentum equations while simulating combustion flow, but energy equations is very vital, that involves very complicated one dimensional equation like this, and there are many models that were evolved. One simple model that involves is the Zeldovich energy equations, that takes care about the variation of in the this enthalpy, which is a function of Cp and T, and Cp also changes during this process, because Cp normally Cp value remains, can be taken to be a constant value within, if it is a 1000 degree, but more than that accuracy drops down. So it has to be both Cp as well as temperature effect has to be included. Then here another term that drops in here, where we call this as a binary which is a diffusion coefficient, and right hand side equation, whatever initial energy it has, final energy is based on the enthalpies of that species with its species flux. So for each species we need to find one term. For each fuel and air mixture you have to find one term. So it's a written in summation form. So it's a very complicated equations. Typically those equations are addressed for each chemical reactions to frame the complete combustion modeling equation. Additionally, when you look at this, when you frame these equations, you also have to look into the diffusion effects during this combustion process. So Fick's law introduces binary diffusion. Now this binary diffusion normally doesn't give sufficient information, so we enter into a concept called multi-component diffusion. And this multi-component diffusion has tremendous effects, which means that the effect of pressure and temperature simultaneously in the combustion domain. Sometimes we will have sometimes one reaction is dominant when the pressure constant dominant with respect to pressure. Some reactions were dominant with respect to low temperatures. Some reactions are dominant with high temperature, which means that reaction type which are formed at low temperature do not show their effect at high temperature, and other way around. So that way it's a very complicated phenomena. We really do not know. We can really did not standardize it with respect to specific fuel. Maybe one end we can say for hydrocarbon fuels, these are the possible reactions. For other types of, because the mostly hydrocarbon fuels can be of two types. One is this there are chemical structure talks about alkyne, alkaline. There are three structures of organic compounds. So that way the equations needs to be resolved for each kind of fuel air combinations. So to address those large temperature effects, there is a term called as Soret effect, which is used when we have large temperatures. And there are some situations when you have thermal diffusions, in which light molecules tries to diffuse from low temperature to high temperature regions, heavy molecules try to come from high to low temperature regions. So these are the quantitative statements that need to be accounted to frame these are qualitative statements that needs to be accounted for to frame the quantitative equations. So what is that multi-component diffusions? So by looking at all kinds of fuel studies, the multi-component diffusions falls in the 4 category. First is ordinary diffusion. So Fick's law only talks about ordinary diffusion, which is mainly due to concentration gradient. One end, that perfume has concentration of perfume is high at one end of the room, but when it spreads, its concentration drops down. So this is ordinary diffusion which can be addressed by Fick's law. Thermal or thermal diffusion. The word thermal diffusion is common term, generic term, but specifically it's a, we call this as a Soret diffusion, because he only framed the effect of those diffusions resulting from combustion, which is mainly due to temperature gradients. So when there is a large temperature gradients, so that Soret diffusion equation is to be taken into account. And typically this is in normal reaction cases, this is a standard case, and in which we have seen that Arrhenius equation, which is a function of temperature. So since it is a function of temperature, so when you say that temperature effect is more predominant than pressure, then we can simply do our analysis or modeling can stop at this point. But then side by side, when you say in a reaction, if the temperature as well as pressure is more significant, because normally when a high speed flows, formation of shock wave is there. The shock wave creates sudden gradient in the pressure as well as temperatures. So pressure effect has to be included. So that way we cannot neglect the effect of pressures. So that has to be included here. Then forced diffusion, which is resulting from unequal body forces. So forced diffusion, we look at a sense that if you look globally at atomic level, if you look at the reactions only at molecular level or atomic level, and try to see when both pressure and temperature effect are so high, we really do not bother whether it is in atomic stage or still it is further, it is in ionic stage or plasma state. So when you say plasma, it's a hot plasma, you don't know, and the role of atoms has no effect. So in one end we have some kind of hot plasma, other domain we don't have, so let's say other domain we still we are in atomic level. So it assumes that this hot plasma acts as a kind of a separate body force that drives the reaction. So it's a both pressure and temperature effects when included, that results in the force diffusion equation. That is the reason it says that it's unequal forces among species. Forces comes from Newton's law, but it's a inertia based situation. But when you say body forces, that comes among species size in the micron level, and if those effects has to be there, then we need to take into account the molecular weight of that atom has no bearing. So that is the reason this unequal body force comes. So what we see here, that if you go from ordinary to forced, the complexity of modeling keeps on increasing. So really you don't have to go for this unless and until pressure and effects are there. So we can stop the standard, if it is simple flame which is burning, we can stop something at this level or this level or this level. So complexity of combustion equation increases. So this is about how the philosophical or viewpoint of the equations. Now coming back to some mathematical treatment, so we have to introduce the terms like diffusion mass flux, diffusion velocities, and since this is represented in terms of so what you see in this equation is two things. One is we need to look into the global picture, and we call this as a mixture, which is, let's say, molecular weight of the mixture. And with respect to species, we also have to find their respective molecular weight. That's the reason I told no mass conservation equation doesn't come here. We have to, and this analysis has to be done on molar basis. Remember, this is on molar basis because this equation has R bar. R is characteristic gas constant. This R bar is universal gas constant, which is true for all kinds of species as well. So all this analysis has to be done in molar basis or molar concentration equation. And here the terms like yi and xi, they are treated as a mole fraction. Okay, this is what we call as a diffusion flux, which is mainly due to concentration effect, which is ordinary diffusion term. And here when we use Dij, we call this as a binary, as a diffusion coefficient, which is with respect to ordinary diffusion. Now when you come back these flux velocities, diffusion flux velocities for species, which is mainly for with respect to temperatures, this equation terms as here it's in a vectorial form. We have temperature gradient, this with respect to this temperature gradient, and that is what we call as Surret equations. It has two terms like its mole fraction, global density, and D stands as diffusion coefficient, and there is a term superscript T, which means this diffusion velocity is due to temperature. So these equations are simple, but the way it has been written, it makes it complicated because we need to address all these points. And again, moving further, this is a combination of all types of equations. And what most important thing that I need to emphasize here, here diffusion velocity due to concentration is given by this. So this has to be taken into account. Now for binary, then you have the term like binary diffusion coefficients for species, species fluxes or diffusion fluxes. Now moving further, I have told that a parameter which has to be defined in a combustion framework, typically it is called as a conserved scalar. By definition, it goes like this: a conserved scalar is any scalar property that remains conserved throughout the flow. Okay, when we say it's a pre-mixed case, obviously we say that the charge is fuel and air concentration remains same. When it is a non-pre-mixed, phi does not give same bearing. So you have to bring another parameter which keeps the fuel identity to be constant throughout this domain. So these explanations we have given: mass fractions, absolute enthalpy, which is typically another kind of a conserved scalar parameters. For with respect to fuel point of view, we will try to define another parameter apart from this equivalence ratio. And here that extra parameter, we call this as a mixture mass fraction. So this mixture mass fraction is defined as a conserved scalar, which is the ratio of mass of the material having origin from fuel stream. Having origin, this needs to be emphasized, origin from fuel stream to the mass of the mixture. Normally when you say phi, it is either mf by ma or ma by mf. But this mixture fraction is represented in a different way. First thing is that one is mass of the mixture, that is by definition. How do you quantify? The mass of the mixture is m mixture. Mass of the material that originates from fuel stream. and for hydrocarbon fuel it is in the carbon and hydrogen. So you take that entity separately, instead of fuel as a whole its molecular weight, you take their identity separately. Okay, so because these sometimes what happens, this mass will be higher, or sometimes carbon mass will be higher, because we don't have same equivalence ratio throughout the flow field. So that way the mixture fraction keeps varying, but mixture fraction may be same, but these masses may vary. Mixture fraction has to be same, but this is varying. So we can model this same mixture fraction everywhere by regulating two terms at a time, MC or MH. So this boils down to a term that when we have a 1 kg of fuel, some mu kg of oxidizer, we get mu plus 1 kg of products. So for that, if you say try to find the mixture fraction, we say for fuel, which is YF, for fuel it's this carbon and hydrogen becomes 1. For products it is 1 by mu plus 1, because here it is here, and for oxidizer this value is 0. For oxidizer there is no carbon, this number is 0. For fuel, that is because if this is reactant, this is products. So complete way, if you find out the mixture fraction of this reaction, we can have this number. So this boils down to a function of YF, which is kg of fuel per mixture, Y product kg of products per kg of mixture. So that way we can find out the mixture fraction for that system. So this is the case where for a 3 species systems. If you have multiple species involving catalyst and others, this number has to be found out, considering the fact in that catalyst whether there is a identity of carbon or hydrogen or not. So these things I have emphasized in the previous lectures, in which I talked about these equilibrium products of combustions involving for a standard hydrocarbon fuels, and we also talked about unimolecular, bimolecular, thermomolecular reactions. We have water gas shift equilibrium and rate equations. So having said this, we talked about these two major curves. One is because we have phi is your equivalence ratio, with respect to this phi, we plot the terms in terms of mole fraction, temperature, equivalence ratio, just to give the things that when we have the major products that comes out when during a lean combustion. Lean combustion it means which is more in air. We see in this case we can say maximum heat release that comes with equivalence ratio phi is 1.05, and through this process when the reaction starts, normally highest temperature the highest temperature is not exactly at 1, it is typically at 1.05, for which maximum temperature is 2278 Kelvin. This is the first curve that we say this is the upper limit of this reaction system during a lean combustion. But what happens now, since we have a flammability limit during an ice engine combustion is 0.8 to 1.2, we see here that how with the one product, that water concentration mole fraction changes with equivalence ratio, and how the CO2 things changes with equivalence ratio. If you see here, nitrogen normally during this region has no effect, and when we have oxygen concentration drops, CO concentration keeps on increasing, because it has to give you CO2. So initially CO concentration increases. When it increases, O2 concentration drops. These two things give CO2, and one point of time the CO and CO2 after that CO2 concentration drops. One point of time they meet at a point. So this is what you see globally. But when you have globally for a lean combustions, but when you have rich combustions, so in that case we expect the the fuel terms are fuel components are higher, so it's a rich combustion. You will find products like which is not seen here, because all these products are radicals like NO, OH, CO. We have simply O term, and with various equivalence ratio their concentrations, there are some concentration keeps on increasing, some are increasing and decreasing. So for example, if this is the case CO, so it starts from this and it goes up to this, and O2 concentration obviously drops when it becomes richer. Hydrogen concentration one point of time increases then comes down. So why I am trying to say is that what is the mechanism, because here also we see there are CO formation, here also we see CO formation here. A very basic difference between these two, we see the CO formation only at higher equivalence ratio. But here if you see, so here we see CO formation, it is at low equivalence ratio. And what is the cause of CO formation at this case? What is the cause of CO formation? Because these two things are contradicting. So that is what we are trying to say. What if to find out cause of CO? This is one particular case study I am saying. Similarly for NO as well. We don't see NO here. Rather you see everywhere we have NO concentration is increasing in this beginning, and towards the later part it drops. Okay. So why these effects are coming into picture? What is the mechanism? So those reasons we need to find out what is called as mechanism of CO formation or NO formation. So this part I will talk later. Here I want to try to emphasize that why, what is the reason for carbon monoxide oxidant, why the CO formation happens. So if you bring the chemistry into it, while bringing the chemistry into it, we bring elementary reactions into picture. So there are two ways the CO formation can be done. That what the chemistry talks about through this when there is water. If it is there are possible elementary reactions that can happen. CO can react with O2 to give CO2, because that is the thing that it has to and the reaction should stop at this point. CO2 when it forms, it has to happen, and it can give AO. So this is how the chain chain, this is what we call as chain initiation sequence. It starts, then when there is a O, it left out O, it tries to see with H2O, it can form these two. This is called as hydroxyl radical formation. Now again in that domain CO is there, it sees OH, it tries to form CO2. This is called main key oxidation reactions. So basically, and then to propagate this chain to form this CO2 completely, this hydrogen and oxygen can react to form this OH. When there is OH, again it tries to see CO, so it will try to form this. So this is a mainly key oxidation reaction. That is what we are supposed to have it. Now in this process, if we see CO and O2, try to find out CO2 and O, its process is slow. When we see, when some reaction, if you can some way make OH, and so that it can take CO to form CO2, So that process is much faster. So it's a basically fast reaction. So normally when you try to reduce the pollutant levels, we try to initiate some kind of branch or chain reaction such a way that we make these reactions to be faster. And at the end of the day, we have to kill this CO to bring bring it to CO2. So this is the concept how we can get CO2 from CO. When CO, another mechanism, it's a is CO through hydrogen. When you try to bring the through hydrogen, if you try to link up, this is complete something called as H2O2 systems. So some way you have to find this kind of these radicals, hydroxyl radicals, and that radicals keeps on propagating. Ultimately, at the end of these things, will land up CO2. This is another mechanism CO can bring to CO2. So while why these equations are important, because these are elementary equations. So in a combustion domain, that is complete hydrocarbon fuels, you have to create some environment has been created or due to its reaction, or you have to initiate some forcibly in this domain to bring completely this CO2. We have to bring it to CO2 come to CO2. Okay, so this is what the mechanism of carbon monoxide formation. Now coming back uh, to nitrogen formation, oxidation of oxides of nitrogen formation, NO formation. So NO formation has some effects. It may be due to two important factors. One is due to equivalence ratio, other is due to its temperature. And in fact, this is main culprits for air pollutions, because nobody wants this. And NO formation can happen in these routes. There are three mechanisms. One is very standard mechanism, which is called thermal mechanism or Geldovis mechanism, which mainly takes Arrhenius equations, and he framed through that binary multi-component diffusion equations, we get these mechanisms. And when you see Arrhenius equations, normally when the environment is 1800 degree and above, this mechanism is realized. We don't feel thermal effect below this. That means it is improper to use these concepts, Geldovis concept, when you don't talk about temperature above 1800 Kelvin. So it's more or less, this is true for all kinds of steady reactions when the temperature is happening above this. Another kind of situation, which is a short duration time scale, millisecond, microsecond time scale, it's a prompt mechanism that during that time also we can have NO formation. That's the reason when you simply ignite, initially for short time you may see nitrogen, after that it vanishes, because dominance of Geldovis mechanism comes into picture due to because initially temperature rises fast, NO started forming, but it suddenly sees high temperature, so this mechanism dominates. So that is the reason when you are looking at that reaction in a very short time scale, this is true. And because of this reason, we see that for rich mixtures we find NO, and N2O is another intermediate mechanism, which normally says that N2O really doesn't have an identity, either it is NO or NO2, and that, but however N2O is a compound that is mainly seen at low temperatures, equivalent lean mixtures. So these thumb rules or rules has to be included whenever we look at whenever you look at a chemical reactions, that is in a broader domain with respect to your equivalence ratio and temperature. And since at this stage we are not looking at the pressure effects because they are in a different domain, shock wave formation and above. So, as a rule of thumb, thermal mechanism is usually irrelevant for temperature below 1018 Kelvin. And with respect to time scale of oxygen formation, NO is formed rather slowly in thermal mechanism. NO is generally formed in the post flame gases. So, these are the inferences that we get out of it. And here I have mentioned why why there is a distinction of different combustion products which is seen in reality for hydrocarbon fuels, and all those mechanisms gives answers to these curves. Now, what is that Jaldovi's mechanism? It here, if you take that reaction in a mathematical form, this how it says how this NO formation happens with nitrogen at this thing. So, they use the rate equations and find, and as if it is a reversible reactions, one can look at the reactions effectively when it moves in a forward direction and when it moves a reverse directions. They would have different value of rate coefficients, and they uses this Arrhenius equations, that is, and this number stands as activation energy for that reaction. And finally, we say it's a function of temperature only. If you really want to find out the concentration of your NO at any point of time, the final equation boils down to this, and this OH and N are concentration of at any of that situation. And why this Fenimore or Pront mechanism? This talks about during this mechanism what happens. So, this is true for when it is for a short time scale and rich mixtures phi up to 1.2. So, before thermal mechanism dominates, NO is formed promptly through CH radicals. Why it is so? Because during initial reaction you may have CH. So, when there is N2 and it sees CH and it initiates the chain reaction, it gives HCN plus N, and then there is a chain sequence reaction. When it sees O, it gives NCO plus H, and all those reactions are reversible. One can it can shift its reaction. Then we have chain sequence reactions, and NO is formed. Now, when this keeps on happening up to when this Jaldovi's mechanism dominates, that means in the domain when temperature rises, these effects are nullified. Okay, this is how what happens during that reaction domain. And there is another point at which is a mainly for use N2O as intermediate mechanisms. So, in N2O mechanism, what we have is this it is important when when we have a fuel lean mixture. When you have a fuel lean mixture, it is typically a low temperature conditions, and it is normally do not seen in IC engine environment. It is seen in the gas turbine environment. This is also similar to NO effect as we see in our previous case. And there are some possibilities that when we are using solid fuels like wood burning, there is a possibility that we can have NO formations. So, solid fuel NO formation are governed by this. This is initiated through this N2O intermediate mechanisms. So O and N2, this gives N2O. N2O, when it sees hydrogen from this fuel, we say it gives NO, and in the chemical form they have standardized a particular route in which we start from fuel, which is a hydrocarbon fuel, and when it gets or experienced with nitrogen from air, these are the possible routes for formation of various atoms and radicals, and ultimately they land off whatever nitrogen we have, it comes as it is, and this also adds to NO here. And this NO also can be killed if you can take them back to this route. So as long as the fuel concentration is reduces, so we keep formulating through this cycle, so that NO formulation is reduced and N2 concentration, which is already there, it improves. So that way we can effectively manage through these chemical processes by reducing the oxides of nitrogen. This is again here point that needs to be emphasized here, that we have NO2 formation, and from NO there is a possibility we can get NO2, and NO2 again can recombine with hydrogen to give NO plus OH. So whatever here I have shown here, OH, NH, all these things are the consequences of this. So what our main requirement is that at high temperature NO2 formation is quite significant. Destruction of this NO2 reaction has become a necessity, and so we need to initiate some kind of catalytic events or mechanisms, or evolve some mechanism through which we can bring down the NO2 level from the atmosphere. Okay. And last slide, I just want to say that whatever I have shown, that is mainly pretending to a case where we commonly encounter typical emission parameters through different chemical reactions involving involving mainly branch reactions, chain reactions, and elementary reactions. And the concept remains true for all kinds of fuels involving this chemical structure, alkynyl fuels. So whenever we have these two terms, hydrogen has a good effect with oxygen because it goes as water, but carbon doesn't have. But because of this carbon, temperature shoots up. When the temperature shoots up, air starts dissociated, so nitrogen effects dominates. Nitrogen it dominates, it gives NO2. So because it's a consequence of one event with other, so basically people are looking at how we can reduce carbon from the fossil fuel. But however, over the statistics so far, hydrocarbons fuels are being used, and complete process starts with methane to any kind of combination of these carbon fuels, and the reaction chemistry for fossil fuels are more or less same. Whatever concept we have introduced, that is also true for any kind of fossil fuels. So for today I will conclude, and these are some sample problems that demonstrates how one can find out diffusion coefficients based on this kind of equations we have encountered here, and this is very vital, and this is nothing but your show rate diffusion. Okay, then we have equations involving diffusional velocity for a multi-component systems. You can see for it only for 3 systems the equations becomes this. If we can n number, and it is analytically possible. When you have n number of equations, you really cannot find out on its own. So programming or matrix form of equation is required. And this is an demonstration that gives the mixture fraction calculations. So in this mixture fraction calculation, which says that for this fuel, you have to find out the carbon and hydrogen identity and write that main equation expression of mixture fraction for each of the constituents. And this mixture fraction calculation will tell you what is the value that remains its identity for all kinds of during the combustion process. So with this I will conclude. Thank you for your attention.